This is the Design Day video for project number 22072, Intelligent Aeroponic Microgravity and Earth Nutrient Delivery System, sponsored by the Biosystems Engineering Department. Our team consists of the following members: Sydney Harrison, Team Lead and Biosystems Engineer; Karen Perkins, Procurement Lead and Biosystems Engineer; Madison Beatty, Mechanical Engineer; Julia English, Mechanical Engineer; and Justice Tiffany, Systems Engineer. This project was brought to us by Dr. Joel Quello from the Biosystems Engineering Department. He was interested in creating a system that can grow crops in terrestrial and extraterrestrial environments, including microgravity, utilizing aeroponic technology. Aeroponics is a technique for growing plants where the roots are suspended in the air instead of soil, and nutrients are delivered to these roots via a fine mist. This technology is cutting edge with an existing patent-pending design from Dr. Quello. The ability to grow crops in microgravity and other extraterrestrial environments is currently being studied on the International Space Station using technologies like the Passive Orbital Nutrient Delivery System, or PONS, which consists of a ceramic-based grow medium and a plant pillow that is watered by a syringe. The idea behind this proposed Amends system is meant to replace these passive crop cultivation systems with a more active, automated aeroponics system. More automation frees up the user's time and energy for other tasks, while giving them more control over the plant's growing environment. This cultivation technology is also scalable and will allow for longer and farther space missions where a replenishable food source will be necessary. The scope of this project was to create a prototype of our sponsor's existing patent-pending idea for the Amends system. Our prototype will serve as a basis for future physical constructions of the system and will demonstrate the technology's functionality. The main features of the patent design are the air and nutrient emitters. Because of the lack of gravity, water becomes very sticky in space. Because of this, air needs to be blown on the plant roots as well as the liquid nutrients to prevent the liquid from fully suffocating the plant's root system. The patent proposed a few different configurations of the emitters, which we considered in our trade design studies.
Our group approached the proposed objective through the following steps. However, our process was not always linear. We took inventory of system requirements, identifying what needed to be present in our system and how we could work to include it. We often came back to these throughout to ensure our progress was lining up with what the sponsor required us to have in our system. To see what was currently being done in the field and what we could borrow or improve upon, we researched similar technologies like the PONS in the International Space Station. After reviewing Dr. Quello's patent, we drafted trade studies to choose a final point design. Once we knew which design we were going to move forward with, we determined a logical flow of subsystems and created our system block diagram. Next, we started on creating actual parts of the prototype by making and testing our critical design elements, manufacturing and ordering necessary parts, constructing the system frame, and creating the code and circuits for the system's automation. The system requirements that we referred to throughout the project are as follows. The Amends system shall use industry-standard aeroponic nutrients, have a collection point for the recycled nutrients, integrate the recycled nutrients back into the nutrient delivery system, have remote-controlled nutrient emitters for the delivery of nutrients to the crops, have remote-controlled air emitters for the removal of excess nutrient solution in the system, be able to grow crops in an environment that is 65 to 75 degrees Fahrenheit, function at variable humidity levels and maintain an optimal value of around 80%, provide a pH to the plants between 6 and 7, have an emergency stop switch, and consist of a transparent containment that allows for viewing the components to ensure they all work as desired. The trade studies mentioned previously are shown briefly here. We came up with 4 different designs, 2 of which are based on the patent, before designing on our final point design, which was heavily inspired by the patent. The first design concept was ultrasonic fogger aeroponics. Design concept number 2 was stationary emitters. Design concept number 3 was aeroponic rock wool. And the chosen point design was design concept number 4, sliding emitters. This design consists of combined nutrient and air emitters that are able to slide laterally along the growth chamber. The sliding feature makes this technology scalable, allowing for even more crops to be grown than the 4 we have demonstrated with the prototype. You will see this in the following slides.
Some of the major features of our final design include the automated sliding air and nutrient emitters, a sensor system connected to a Raspberry Pi, and waste recycling. The lid is removable and contains 4 circular holes that fit net pods the plants sit inside. On the left side of the frame sits a PVC pipe container that holds our nutrients to be sprayed through the emitters into the plants. The lateral sides have belts to allow movement and a rubber zipper system to keep the container airtight while allowing the tubing to get inside the growing chamber. Here are previous iterations of our design that we have improved upon based on sponsor feedback to create our final design. The logical flow of our subsystems is shown in our system block diagram, and our system software diagram shows how the user can influence the system through the graphical user interface and touchscreen. The major parts we manufactured on our own were the acrylic system frame, the PVC pipe nutrient container, and the emitter holders. The frame was created in the fabrication shop, and the emitter holders were 3D printed in campus at the makerspace.
Here is the progress of the project up to this point. We are wrapping up the frame building while the plants are germinating. Our 3D printing and circuit creation is complete. We are just waiting on a few delayed items to be delivered before our entire system can be put together and tested. During the course of this project, we did face challenges and learned some lessons from those obstacles. A few challenges we ran into included multiple 3D printing failures, some of which were avoidable and others that were printer malfunctions. We also experienced procurement delays related to supply chain issues. Lastly, our group experienced some problems with communicating properly toward the back end of the project once we split into sub-teams to multitask. The lessons we learned from these challenges are that communication is so important and should be prioritized through the entire process. Over-communicating is better than the alternative. We also could have benefited from starting to build the mechanical and electric components sooner to give us more time to make mistakes and have delays. Procurement delays could have also been mitigated in the future by starting sooner and figuring out all the necessary purchases at the beginning. Our group could have also benefited from more prototyping and testing to provide even more confidence in our design. We hope that our prototype of Dr. Quillo's design propels projects like this forward and benefits further research on crop cultivation techniques for long-term space missions. Once we unlock the ability to grow plants in space efficiently, there will be few limits to where in space we can explore. Our team would like to thank the following people for their contributions to this project. Our sponsor, Dr. Joel Quillo, for trusting us with his project. Our mentor, Doug May, for supporting us through the entire length of the project. Mike Mason for guiding us in the biosystems fabrication shop and giving design advice. And Catalyst Studios staff members, especially Alyssa Woods, for assisting us with 3D printing. Thank you for watching.